Welcome back. In this video, we're going to talk about confidence intervals for a population proportion. If you haven't watched the other two videos on this topic, I highly recommend you do so before watching this one. We're going to pick up where we left off. So in the last video, we talked about how to find the probability of observing a sample proportion at least as extreme as some value. In this video, we're going to do the opposite. Let's say we want to find the values between which 95% of our sample proportions fall. Since this range should be symmetrical, the boundaries can be found by adding and subtracting the same value from the mean. Specifically, we're going to add and subtract some number of standard deviations. The number of standard deviations is determined by z-critical, which depends on the confidence level. The values for z-critical can be found using a t-table. It's located at the bottom, and here's a sample of what a few entries might look like. Plugging in this value for z-critical, as well as our mean and standard deviation from the first video, we find that our lower and upper boundaries of the 95% region are 0.504 and 0.696. Let's also walk through how to do this on a TI-84. Start by pressing second, then vars to open up the menu of distributions. Then press 3 to open up the screen for inverse normal. After plugging in the relevant values, paste, then compute the function to find the same interval that we obtained earlier. If we collect a sample and we want to find the confidence interval for a population proportion, we would go through the same steps, except that we would use the sample proportion p hat in place of the population proportion p. A couple of things worth mentioning are that the standard deviation calculated with the sample proportion is referred to as the standard error, and the distance from the sample proportion to either boundary of our confidence interval is called the margin of error, which is just the value for z-critical multiplied by the standard error. Let's say we sample 100 students and find that 64% of them use max. If we want to find the 95% confidence interval for the population proportion, we could follow the steps again shown previously, but I'm going to show you how to do it on a calculator. Start by clicking Stat and then tabbing over twice to Tests. Once you're there, you can scroll down until you get to 1-prop_z_int, or a shortcut is you can click alpha and then math to jump to the screen. When you're inserting the values, x represents the number of successes, or in this case the number of MAC users in your sample, n is the sample size, and c level is your confidence level. After calculating, we find that the lower boundary of our confidence interval is 0.546 and the upper boundary is 0.734. The correct interpretation is that we are 95% confident that the true population proportion is within the interval obtained. It's important to note that we cannot say there's a 95% probability that the true population proportion is within the interval. If you're curious as to why, Google it, dork. On the left is a graphical representation of the confidence interval. Since we happen to know the true population proportion, I've overlaid it onto the visualization as a dotted blue line. I think a better way to think about confidence intervals is to observe what happens when we generate many. On the screen are 20 intervals, and what you may notice is that 19 of them contain the true population proportion, and one of them has missed it. 95% confidence means that if we generate many confidence intervals from many samples, roughly 95% of them should contain the true population proportion. Take a moment to make a prediction. How might confidence level affect the width of a confidence interval? For reference, here's that segment of the t-table shown earlier. Working through this step by step, we find that if we raise our confidence level, then our value for z-critical also goes up. From the formula, if z-critical increases, then so does the margin of error. And if our margin of error increases, then our confidence interval is wider. Altogether, this means that if we raise our confidence level, then the width of our confidence interval also goes up. If we decrease our confidence level, then we will have a narrower confidence interval. This makes sense, because if we want to say that we're really confident about where the population proportion is, we'll generate really wide intervals to decrease our chances of being wrong. To illustrate this, here are two examples of intervals generated with 95% confidence and 75% confidence. Now take a moment to predict how the sample size would affect the width of the confidence interval. Starting off, we can see that if we increase the sample size, then we decrease the standard error. This occurs because the sample size, little n, is in the denominator of the fraction. And if our standard error decreases, then our margin of error is smaller. Lastly, if we have a smaller margin of error, then we have a narrower confidence interval. Altogether, increasing the sample size decreases the width of the confidence interval, and if we decrease our sample size, then we have a wider confidence interval. Once again, here are a couple of intervals generated with different sample sizes to illustrate this point. Let's say we have a desired margin of error at a certain confidence level. How might we find the sample size, little n, needed to achieve it? So in this example, we're going to look at how many students we must sample if we aim to create a 95% confidence interval with a margin of error of 10%. Let's start with the formula for margin of error and work our way towards solving for n. We can start by dividing both sides by z-critical, then squaring both sides, multiplying both sides by n, and then multiplying by the inverse of the fraction in order to get n by itself. Filling in our values for z-critical as well as the margin of error are pretty straightforward, but in this scenario we don't have access to a sample proportion p hat yet. What we do instead is we fill in a sample proportion of 50%, which represents the most conservative estimate. This produces a sample size of 96.04. But this is wrong because the sample size must be an integer. We cannot have a fraction of a student unless they're really small. If we round down, we might produce a margin of error that is greater than 10%, and that's not what we're asking for, so we must round up. So we'll modify the original formula to include ceiling brackets. They just mean whatever's inside, rounded up to the nearest integer. So we get a sample size of 97 individuals that are needed to create a 95% confidence interval with a maximum margin of error of 10%. That's all I have for now. Once again, here's a few practice problems to test your knowledge so far. Feel free to share your solutions in the comment section below, and stay tuned for an upcoming video on hypothesis testing.